So in this question, we're told that Joe and Keith are carrying out an experiment. A bag contains a large number of counters, some of which are green. Keith randomly draws a counter from the bag, records its color, and then replaces it before drawing the next counter. He continues until he has drawn 2 counters. The random variable x represents the number of draws up to and including the second green counter. Okay, that statement there, that's what's let me know we're likely working with the negative binomial distribution. We weren't just looking for the first success, we were looking for 2 successes, 2 green counters. The random variable y represents the number of draws up to and including the first green counter. Okay, and there it is, the geometric distribution. We were only looking for the first success. We have the negative binomial for x and geometric for y. On each occasion, it records the value of x and the value of y. They repeat this process a large number of times. First, we're asked to state an appropriate distribution to model the random variable y. So as I said, y is going to be a geometric distribution with an unknown probability of p. Looking at the data, Joe suggests that the variance of x might be equal to the square of the mean of x. Given that x may be modeled by the negative binomial distribution, so they actually told us it was negative binomial, no marks for that. Explain why Joe's suggestion cannot be true for the underlying distribution. Okay, so let's go back and look at Joe's suggestion. So Joe suggested that the variance of x equals the square of the mean of x. So if that was true, then the variance of this negative binomial distribution, so RQ over P squared, will equal the expectation of the negative binomial distribution, R over P squared. Well, that's going to be R squared over P squared. Denominators are the same, so we're really saying RQ equals R squared. If that's true, let's actually focus on this instance. We wanted 2 successes. So 2q is equal to 2 squared. So 2q equals 4. That means q must equal 2. If q equals 2, so the probability of failure is 2, the probability of success is 1 minus q. The probability of success is 1 minus 2 or negative 1. Well, this is all kinds of wrong. P and Q are both probabilities. Probabilities have to range in between 0 and positive 1. And straight away, both of these are outside of that sensible range of probabilities. So our initial underlying assumption that variance of x equals the expectation of x squared cannot be true. Before part C of the question, we're told that Joe uses the data and estimates that the variance of y is 20. We're asked to calculate an estimate for the proportion of green counters in the bag. Okay, let's use information. If the variance of y is 20 and y is now the geometric distribution, that means q over p squared equals 20. Let's rearrange and solve. Multiply by the p squared, we get q equals 20p squared. And as always, this quadratic can be solved. When we solve, we get 0.2 and negative 0.25. Just as we saw before, a negative will be meaningless, so it must be 0.2 we're working with. P equals 0.2. That's the probability of success. That's the proportion of green counters in. Ahead of part D, we're told that in a different bag, 40% of the counters are green and the rest are red. For this new bag, we're asked to calculate the probability that the second green counter occurs on the 5th draw, given that the first green counter occurs on the 2nd draw. Now this is interesting. Let's go ahead and plot out the 5 different outcomes. What can happen each time? We know that the 5th attempt is a success and the 2nd attempt is a success. All the others are failures. So here's the 5 attempts and what the outcomes are. Now, this is a given question. So given that the first green counter occurs on the 2nd draw, Well, we know that's what happened. We're no longer interested in the first two draws. We know that those things really happened. The only things that have any variability to them, the only things that have a changeable outcome are attempts 3, 4, and 5. So that means there's only 3 attempts and 1 success. So actually, this is a geometric distribution. And we want to know the probability our success occurs on the 3rd attempt. So the probability that T equals 3, 2 failures and 1 success. 1, 4, 4. Now, we could have done this the long way around with intersections and dividing by the given part, but actually, if we have a visual, we know that we can narrow our scope of interest to just these 3 outcomes and then work out what's going on from there. Just like we do in straight maths, a good diagram, we can narrow it down. We're only interested in these 3 outcomes.